Hello everyone, my name is Rafael Makrigiorgis and I am a software engineer at KIOS Research Center of Excellence at the University of Cyprus. Today I'm going to present to you our paper on how to enhance vehicle detection for a more efficient road traffic monitoring using aerial cameras. Road traffic monitoring is a really important component of intelligent transportation system. Therefore, information gathered from traffic monitoring can determine areas with high traffic congestion that have to be addressed. Existing sensing technologies are either costly or difficult to install in existing infrastructure. Hence, there is a need to revolutionize the intelligent transportation sector, and one way to do this is by utilizing unmanned aerial vehicles. Some of the benefits are that UAVs are affordable, easy to capture data with, and they can be combined with advancement of computer vision and deep learning techniques. Existing approaches for aerial traffic monitoring mainly focus on utilizing object detection methods, which in some cases can lead to fault detections and messed up traffic data, such as this image. Even if we improve the underlying object detection methods, such errors can still happen. In this work, we integrate the road segmentation method in order to provide context to the vehicle detection in an attempt to tackle these issues and enhance and improve the overall traffic monitoring by focusing only on the regions of interest. An overview of our proposed framework. A frame from the drone is passed into the segmentation network and outputs a road mask. This mask is then applied onto the frame to include only a road segment in order to have a targeted detection. It is then passed through the detection network in order to detect vehicles on the road only. Then, using the vehicle's bounding boxes, we are correcting the mask in order to fill in any missing gaps. Furthermore, the whole process continues for the consecutive frames by continuously correcting the mask using the detections. The vehicle detection and classification were experimented using the YOLO family of networks. Post-processing of the detections is done to find temporal association and consistency. It is implemented utilizing Hungarian algorithm using intersection over union scores, KD trees for distance matching and optimization, and Kalman filter for tackling some occlusions and have a more precise tracking. Also, tracklets are classified as active or inactive based on some consistency rules. Furthermore, direction of the vehicle is estimated using trajectory subtraction, and the velocity is estimated using ground sample distance algorithm for estimating pixel per kilometers and by calculating the clean distance covered of each vehicle over time. The datasets used for the detection were partly from footage captured by our own UAV flights, UAV NDT, IRRKD, and some UAV videos that were captured for evaluation. For the segmentation, OpenStreetMap and ArialKD datasets were used. Initially, the datasets were trained without the ArialKD dataset in order to decide which models to use, and as it seems, for the detection, Tiny Yellow V4 with 3 layers is the most balanced in terms of accuracy and performance. For the segmentation, Resonate 18 FPN was the best option. Then both models were retrained on the ArialKD dataset as well to evaluate the performance of the detection on KD testset, with and without the help of the segmentation mask. As it seems, the overall results are around 20% better with segmentation. To evaluate the whole framework, static aerial footages were captured around Nicosia city where both parked and moving vehicles were found. As shown in this graph, the number of vehicles drastically influences the time required to perform the associations and Kalman filter updates and thus reduces the overall frame rate. By applying the mask, in the first example below for instance, it reduces the number of vehicles from 155 to 70, which is an increase from 9 FPS to 19. The average FPS with the mask is around 20 and without it is around 8. The vehicle accuracy was around 98, which means the segmentation does not hinder the vehicle detection. This was also tested in real time with a live stream from a UAV in order to verify that it's working in real time as well. This graph depicts the post-processed traffic data from that experiment, showing the average velocity and average density of vehicles over time. To conclude, we introduced a deep learning pipeline for road traffic monitoring from aerial video. It is an efficient and more focused traffic information gathering tool, and with the help of the segmentation mask, it improves the performance by 2 times. As for future work, we would like to integrate the detection segmentation into one network in order to avoid redundant processing and improve generalization. We would like also to add more consistency rules for occlusions, to expand our dataset, to improve furthermore the performance, and to estimate more traffic data during the framework process. Thank you for your attention.